somewhere in the constellation Cygnus, roughly 6,000 light-years from Earth, there is a star being slowly torn apart by something no telescope has ever directly seen. Astronomers first noticed it in 1964 as an unusually bright source of X-rays, and it took nearly a decade of argument before most of them agreed on what they were actually looking at. Not a star, not a nebula, but a hole in the fabric of space itself, so dense that light cannot climb back out of it. That object, now known as Cygnus X1, became one of the first black holes most scientists were willing to accept was real, and it was only the beginning. Tonight we go looking for 200 more facts about these objects. How they form, how large they can grow, what would actually happen to you if you fell into one, and the handful of questions about them that remain, even now, genuinely unsolved. Some of what follows is measured with extraordinary precision. Some of it sits right at the edge of what physics can currently explain. We'll be honest about where that line falls as we go. The simplest way to understand a black hole starts with a much older idea: escape velocity. Any object with mass has a speed you'd need to reach to break free of its gravity entirely. For Earth, that's about 11.2 kilometers per second, which is why rockets need to go so fast to leave the atmosphere behind. In 1783, an English clergyman and geologist named John Michael wondered, in a paper read aloud to the Royal Society, what would happen if a star were massive and dense enough that its escape velocity exceeded the speed of light itself. Michel calculated that such an object would be invisible, because even light couldn't outrun its gravity. He called the idea a dark star, and for over a century, it remained a curiosity rather than a serious prediction, largely forgotten until Einstein's general relativity gave the concept a mathematical home it had never had. In 1915, Einstein published his field equations describing gravity not as a force in the traditional sense, but as the curvature of space and time caused by mass and energy. Barely a month later, while serving on the German front during the First World War, a physicist named Karl Schwarzschild found an exact solution to those equations, describing the gravitational field around a single non-rotating spherical mass. Buried inside that solution was a specific radius, now called the Schwarzschild radius, at which the mathematics broke down in a very particular way. If all of an object's mass were compressed inside that radius, nothing, not even light, could ever escape from within it again. For the Sun, that radius works out to about 3 kilometers. For Earth, it's roughly 9 millimeters, meaning if you compressed the entire planet into a sphere smaller than a marble, it would become a black hole. The boundary at that radius is what we call the event horizon, and it's worth being precise about what it is and isn't. It is not a physical surface. There is no wall, no membrane, nothing you could touch or bump into. It is simply the point of no return, the last location from which light can still travel outward and eventually reach a distant observer. Cross it, and every possible path forward, in the language of general relativity, points only inward, toward the center. Some physicists describe it less like a barrier and more like a waterfall. The water itself doesn't change at the edge, but past a certain point, no amount of swimming upstream will get you back over the falls. At the very center of a black hole, according to the equations, is the singularity, a point, or in the case of a rotating black hole, a ring, where the curvature of space-time becomes infinite, and our current physics simply stops giving useful answers. This is one of the most honest things to say about black holes. General relativity predicts something happens at the singularity, but it also predicts its own equations break down trying to describe it, which most physicists take as a sign that a deeper theory, one that successfully merges gravity with quantum mechanics, which we don't yet have, would replace that infinity with something more physically sensible. We'll return to that unresolved tension later in the video, because it turns out to be one of the most important open questions in all of physics. It took decades for the physics community to accept that objects like this could actually exist in nature, rather than being a mathematical oddity. Einstein himself, in a 1939 paper, argued that stars couldn't actually collapse all the way down to the Schwarzschild radius, believing some unknown physical process would halt the collapse first. It was the physicist John Wheeler, ironically one of the people who had been skeptical for years, who popularized the term black hole itself, using it publicly for the first time in a 1967 lecture, after a member of his audience reportedly suggested the phrase. Before that, physicists had used more awkward terms like gravitationally completely collapsed object, which, whatever its scientific precision, never had much chance of catching on. It's worth pausing here on a detail that surprises many people. A black hole is not a cosmic vacuum cleaner, indiscriminately sucking in everything nearby. From a safe distance, a black hole's gravity behaves exactly like the gravity of any other object of the same mass. If our sun were somehow replaced with a black hole of identical mass, Earth's orbit would not change at all. We'd simply lose our source of light and heat and freeze in the dark, still circling the same empty point in space we always had. Black holes are dangerous specifically because of how compact they are, not because their gravity is somehow stronger than ordinary gravity at the same distance. One more foundational fact worth sitting with: nothing about a black hole's formation destroys mass or energy in any way physics currently understands. The matter that falls in doesn't disappear from the universe's accounting. Its gravitational, electric, and rotational effects persist, measurable from outside, even though the matter itself is, in a very real sense, gone from view forever. What that matter's ultimate fate actually is, once it crosses the horizon, remains one of the genuinely open questions we'll spend real time on later tonight. Before we go any further, it's worth explaining why a channel like this one takes this particular shape. Long, unhurried, meant to be listened to with the lights off, rather than watched with your full attention. If tonight's descent into the physics of black holes is helping settle your mind towards sleep, subscribing costs nothing. And it's the simplest way to keep this channel making more of these. Now back to the edge of the unknown. For now, what matters is simply this: an object whose gravity is so complete that light itself cannot escape it was once considered a mathematical fantasy too strange to be physically real. Then astronomers started finding candidates for exactly that fantasy scattered across the sky, and the question stopped being whether black holes exist and became a much longer, still unfinished list of questions about what they actually do. One of the most elegant results in all of black hole physics is a principal physicist, John Wheeler, the same physicist who popularized the term black hole itself, later helped formalize into what's informally called the no-hair theorem. The idea is that no matter how complicated, how lumpy, or how chemically exotic the star or cloud of matter that collapses to form a black hole originally was, the resulting black hole itself can be completely and entirely described using just three numbers: its mass, its electric charge, and its spin. Every other detail about the object that fell in, its composition, its shape, whether it was made of hydrogen or gold or spacecraft parts, is, according to general relativity, erased from the outside universe's perspective entirely, radiated away, or otherwise lost as the black hole settles into its final, simple state. Physicists sometimes describe this by saying a black hole has no hair, meaning no additional distinguishing features or texture beyond those three basic numbers, an unusually clean and almost anticlimactic result for objects that form through some of the most violent and chemically complicated processes in the universe. The no-hair theorem was worked out in stages during the 1960s and 1970s through combined contributions from physicists including Werner Israel, Brandon, Carter, and Stephen Hawking himself, and it remains one of the most surprising and mathematically well-established properties of black holes in classical general relativity, even though, as later chapters of tonight's video will explore, it sits at the very heart of the information paradox, since it's precisely this erasure of detail that makes it so difficult to explain how information about what fell in could possibly be preserved. Carl Schwarzschild's own circumstances, when he derived his famous solution, deserve a moment of attention, since they add a genuinely poignant layer to one of the field's founding results. Schwarzschild produced his calculation in late 1915 while serving as an artillery officer on the Eastern Front during the First World War, having volunteered for military service despite already being in his 40s and an established, internationally respected astronomer, calculating trajectories for German artillery units by day and working through Einstein's newly published field equations, apparently in his own time, in between. Schwarzschild mailed his solution directly to Einstein, who was sufficiently impressed to personally present the paper to the Prussian Academy of Sciences on Schwarzschild's behalf in early 1916, since Schwarzschild himself remained at the front. Schwarzschild contracted a rare and painful autoimmune skin disease called pemphigus while serving in the war, and he died from complications in May 1916, only a few months after completing the work that would eventually give his name to the most fundamental radius in all of black hole physics, never living to see the term black hole coined, the concept accepted as physically real, or any of the observational confirmations that would eventually follow. A genuinely striking case of a scientist's most consequential contribution to physics being derived and published in the final months of an unrelated, ultimately fatal wartime service. There's a genuinely subtle technical distinction worth including here, one that trips up even some physicists working outside the specific subfield of numerical relativity. The event horizon most people picture, the sharp absolute boundary separating escape from no escape, is technically defined only in terms of a black hole's entire future history, meaning identifying its exact location, in the strictest mathematical sense, requires knowing everything that will ever fall into the black hole for the rest of time, an inherently retrospective definition that makes it surprisingly awkward to use directly inside a real-time computer simulation of a forming or evolving black hole. Researchers who model black holes numerically generally work instead with a related but distinct concept called an apparent horizon, defined using only the local curvature of space-time at a single moment, without requiring any knowledge of the future at all. A definition that can be calculated directly from a simulation's current data, and that, under a wide range of physically reasonable conditions, sits at or very close to the true event horizon's location, without being mathematically identical to it in every conceivable scenario. This distinction remains largely a technical bookkeeping matter for working physicists rather than a genuinely open scientific mystery. But it's a useful reminder that even a concept as seemingly simple and final as the point of no return carries more mathematical nuance underneath it than the everyday, popular description usually lets on. Not every black hole forms the same way, but the most common and best understood path begins inside a massive dying star. For most of a star's life, it exists in a delicate balance. The inward pull of its own gravity is matched by the outward pressure generated by nuclear fusion in its core, hydrogen fusing into helium, releasing the energy that makes stars shine. This balance can hold for millions or billions of years, depending on the star's mass, but it is never permanent because a star is slowly consuming the very fuel that holds it up against its own weight. For a star significantly more massive than our Sun, astronomers generally put the threshold at roughly 20 times. The Sun's mass, though the exact figure depends on composition and other factors, the ending is dramatic. As the core exhausts its hydrogen, it begins fusing progressively heavier elements, helium into carbon, carbon into neon, working its way up the periodic table in stages that get shorter and shorter, sometimes lasting only days by the time the core is fusing silicon into iron. Iron is the critical turning point because fusing iron doesn't release energy, it consumes it. Once a massive star's core turns to iron, the fusion reactions that had held it up for millions of years simply stop being able to produce outward pressure, and the core collapses catastrophically in well under a second. That collapse triggers a supernova, one of the most energetic events in the observable universe, briefly outshining an entire galaxy of hundreds of billions of stars. The outer layers of the star are blasted outward at tremendous speed, while the core itself continues collapsing inward. What happens next depends almost entirely on how much mass is left in that collapsing core. If the remaining core is between roughly 1.4 and about 3 solar masses, it typically collapses into a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons, held up against further collapse by quantum mechanical pressure between neutrons. But if the remaining core exceeds roughly 3 solar masses, a limit named after physicists J. Robert Oppenheimer and George Volkoff, no known force can stop the collapse. The core keeps shrinking, past the density of a neutron star, past every known state of matter, and becomes a stellar mass black hole. Cygnus X1, the object we opened tonight's video with, is believed to be exactly this kind of black hole, roughly 21 times the mass of our Sun, orbiting a massive blue supergiant companion star that is slowly feeding it material, which is precisely why it glows so brightly in X-rays. Not because we can see the black hole itself, but because matter spiraling toward it is heated to millions of degrees by friction before it disappears across the event horizon. The confirmation of Cygnus X1's nature took years of careful measurement of its companion star's orbital motion, work that earned physicist Stephen Hawking a famous and famously good-natured wager with fellow physicist Kip Thorne in 1974, betting against the very existence of the object he had spent years theorizing about. A bet Hawking conceded in 1990, once the observational evidence became overwhelming. It's worth noting that this stellar collapse pathway can only produce black holes within a certain mass range, generally estimated at somewhere between about 5 and perhaps 100 solar masses for so-called stellar mass black holes. And even within that range, the exact relationship between a dying star's initial mass and its resulting black hole's final mass remains an area of active research, complicated by how much material a star sheds through stellar winds and eruptions before it ever reaches the point of collapse. Some massive stars are believed to lose so much of their outer material during their lives that what's left behind at the moment of collapse produces a smaller black hole than a naive read of the star's original mass would suggest. There's a genuinely strange detail worth including here. Astronomers have observed, in a small number of cases, massive stars that appear to simply vanish from view without the expected accompanying supernova explosion, a phenomenon some researchers have proposed could represent a failed supernova, where the core collapses directly into a black hole so efficiently and so completely that the shock wave never manages to blow the star's outer layers away in the usual visible fireworks. One well-studied candidate for this, a red supergiant called N6946BH1 in a galaxy roughly 22 million light-years away, was observed brightening modestly and then disappearing entirely from telescope images over the following years, consistent, though not definitively proven, with exactly this kind of direct collapse. The strange part of stellar mass black hole formation, when you sit with it, is the sheer violence of the transition contrasted with the silence of the result. A star's collapse into a black hole takes a fraction of a second, releases more energy in that instant than the star produced through its entire multi-million-year life, and then leaves behind an object that, from the outside, does almost nothing at all. No light, no radiation of its own, simply a region of intensely warped space, quietly orbiting wherever gravity carries it, sometimes for the remaining lifespan of the universe itself. some of the most violent black hole formations produce a second, entirely separate class of astronomical event, one so bright it can be detected from nearly the edge of the observable universe. Long-duration gamma-ray bursts. Astronomers now generally attribute these bursts to what's called the Quasar model, first developed in detail by astrophysicist Stan Worsley in the early 1990s and refined considerably since, in which an especially massive, rapidly rotating star's core collapses directly into a black hole, while the star's outer layers are still falling inward, rather than having already been blown away by an earlier, more ordinary supernova explosion. In this scenario, infalling stellar material forms a brief, extraordinarily hot accretion disk around the newly formed black hole, and a narrow, ultra-relativistic jet of particles, launched along the star's rotational axis by a mechanism related to the same magnetic processes, discussed later in tonight's video, burns straight through the collapsing star's own outer layers and out into space, producing a beam of gamma rays so intense that, if it happens to point directly at Earth, it can be detected across billions of light years, despite lasting only seconds to minutes. The specific link between long gamma-ray bursts and newly forming black holes was confirmed observationally through several well-studied events since the early 2000s, in which astronomers detected a burst's initial gamma-ray flash, then pointed follow-up telescopes at the same location, and captured the fading light of an accompanying supernova explosion. Arriving days later, direct evidence tying the two phenomena to the same underlying stellar collapse, precisely what specific combination of a progenitor star's mass, rotation rate, and magnetic field strength, capable of piercing all the way through the collapsing star, rather than being smothered before ever reaching the surface, remains an active subject of ongoing simulation work. Since only a small fraction of black hole-forming stellar collapses appear to produce a detectable gamma-ray burst at all. Not every sufficiently massive star is an equally likely candidate for producing a black hole, and astronomers have found that a star's own history of shedding material before its final collapse matters enormously to its eventual fate. Wolf-Rayet stars, a specific class of extremely hot, massive stars, first catalogued in 1867 by French astronomers Charles Wolf and Georges Rayet, are characterized by exceptionally powerful stellar winds that strip away their outer hydrogen layers at a ferocious rate, exposing the hotter helium-rich material underneath, and losing, over the course of their comparatively brief lives, a substantial fraction of the total mass they started out with. Because so much material is shed before collapse ever occurs, the specific relationship between a Wolf-Rayet star's original birth mass and the eventual mass of the black hole it leaves behind is considerably less straightforward than a simple, direct proportion, and astronomers modeling stellar evolution have found that two stars born with dramatically different initial masses can, after sufficiently different histories of wind-driven mass loss, end up producing black holes of surprisingly similar final size, while conversely, stars of similar starting mass but different metal content, since heavier elements strengthen a star's stellar wind considerably, can end up producing final black hole masses that differ substantially from each other. This complicated relationship between birth mass and final black hole mass is one of the specific reasons astronomers were genuinely surprised by some of the larger black hole masses gravitational wave detectors have measured since 2015, since those larger masses have pushed researchers to reconsider just how much mass a massive star actually reaching through to the moment of collapse under specific, less wind-stripped conditions, particularly in the lower metal environments believed to have been more common earlier in the universe's history. A newly formed black hole doesn't necessarily stay put at the location of its parent star's collapse, and astronomers have found evidence that the supernova process itself can impart what's called a natal kick, a sudden burst of asymmetric velocity given to the resulting compact object, If the surrounding explosion happens to blast away material unevenly in one particular direction, an imbalance that, through simple momentum conservation, sends the newly formed black hole recoiling in the opposite direction at speeds that have, in some observed cases, been estimated at hundreds of kilometers per second. This natal kick phenomenon was first confirmed and studied in considerably more detail for neutron stars, since several are observed as pulsars moving unusually fast relative to their surrounding stellar neighborhood. But researchers have since found indirect evidence for similar kicks affecting black holes as well, including specific binary star systems in which a black hole's current orbital path and velocity appear difficult to fully explain unless its formation included a genuine one-time asymmetric kick rather than a perfectly symmetric collapse that would have left the resulting black hole moving smoothly along its progenitor star's original pre-existing orbital path. A sufficiently large natal kick can, in some modeled scenarios, be strong enough to eject a newly formed black hole from a binary system entirely, or even, in especially extreme cases, from its host star cluster altogether, sending it drifting alone through the surrounding galaxy as one of the isolated black holes discussed later in tonight's video, a genuinely violent parting gift from the very same explosive process that brought the black hole into existence in the first place. The very first stellar mass black hole widely accepted by the astronomical community, setting aside Cygnus X1's own decade of lingering argument discussed at the start of tonight's video, illustrates just how long and how methodical the process of confirming any single black hole candidate can be. Cygnus X1 was first detected as an X-ray source in 1964 during a brief sounding rocket flight, rather than from any permanent observatory, and it took the combined work of numerous research teams across the following decade, carefully measuring its blue supergiant companion star's orbital wobble, estimating the companion's own mass from its stellar classification, and using basic orbital mechanics to work out how much unseen mass its invisible partner needed to have before the case became strong enough that most working astrophysicists were willing to set aside more conservative alternative explanations, including the possibility that the X-ray source might instead be an unusually dim ordinary neutron star rather than something requiring an entirely new category of object. This deliberate, multi-year process of ruling out every reasonable alternative before finally accepting the more extraordinary explanation has become something of a recurring pattern across the history of black hole astronomy more broadly, repeating in slower or faster form for Sagittarius, for the intermediate mass candidates discussed earlier in tonight's video, and for essentially every gravitational wave detection LIGO has announced since 2015, each requiring its own careful, methodical elimination of more mundane explanations before the collaboration was willing to publicly declare a genuine black hole merger had actually been observed. Not all black holes share the same origin story, and one of the more interesting open questions in astrophysics involves the different size categories they seem to fall into, and the awkward gaps between them that observations haven't yet fully filled in. Stellar mass black holes, the kind formed by collapsing massive stars discussed in the last chapter, typically range from around 5 to perhaps a few dozen solar masses, though gravitational wave detectors have found merging black holes at the higher end of that range that surprised many astrophysicists when first observed in 2015, suggesting the upper limit of stellar collapse may be higher than earlier models predicted. At the opposite extreme sit supermassive black holes ranging from hundreds of thousands to tens of billions of times the mass of our Sun, and these appear to reside at the center of nearly every large galaxy. Astronomers have carefully studied, including our own Milky Way, which we'll examine in detail in the next chapter. How supermassive black holes originally formed remains a genuinely open question in astrophysics. The timeline is tight because astronomers have detected supermassive black holes already fully formed within less than 1 billion years of the Big Bang, which is uncomfortably fast for the standard picture of a black hole growing purely by consuming stellar material and merging with smaller black holes over cosmic time. Several competing theories have been proposed. Some researchers suggest they grew from unusually massive seed black holes formed by the direct collapse of enormous primordial gas clouds, bypassing the stellar formation step entirely. Others propose rapid, repeated mergers of stellar mass black holes in the dense stellar clusters common in the early universe. Neither explanation has been definitively confirmed, and the honest answer, as of current research, is that astronomers are still working out precisely how the universe managed to build black holes billions of times more massive than the Sun within its first billion years of existence. Between these two extremes sits a category astronomers call intermediate mass black holes, theorized to range from roughly 100 to 100,000 solar masses. And for decades, this middle category was frustratingly difficult to confirm observationally, leading some researchers to wonder whether it was simply an empty gap in nature. A size range black holes rarely, if ever, occupy, that began to change with more sophisticated detection methods. A particularly compelling candidate, catalogued as HLX-1, located in a galaxy about 290 million light-years away, is estimated at roughly 20,000 solar masses based on its X-ray emissions, and gravitational wave detectors have since captured merger events producing black holes that land squarely within this intermediate range, lending increasing observational support to a category that was, for a long time, based mostly on theoretical expectation. There is also a more speculative, unconfirmed category worth mentioning honestly: primordial black holes, theorized to have formed not from collapsing stars at all, but from extreme density fluctuations in the first fractions of a second after the Big Bang itself, potentially spanning an enormous range of masses, from smaller than an asteroid up to stellar scale. No primordial black hole has ever been directly confirmed to exist, and the idea remains a hypothesis, though an intriguing one, because some physicists have proposed that sufficiently small, undetected primordial black holes scattered throughout galaxies could potentially account for some portion of the universe's dark matter, the mysterious, unseen mass that makes up roughly 85% of all matter in the cosmos. It's an elegant idea specifically because it wouldn't require inventing an entirely new type of particle, only extending a phenomenon we already know exists. Current observational constraints, largely from gravitational lensing surveys that would detect the light-bending signature of these objects passing in front of background stars, have ruled out primordial black holes as the sole explanation for dark matter across most, though not quite all, of the mass ranges where they might otherwise hide. Astronomers have also begun distinguishing black hole populations by how they were formed and what environment they occupy. Solitary, black holes drifting through interstellar space with no visible companion, a population that recent gravitational microlensing observations have started to detect directly for the first time. Black holes locked in binary systems with ordinary stars, like Cygnus X1, and black holes embedded within the dense cores of globular star clusters, where gravitational interactions between thousands of closely packed stars over billions of years appear to be an efficient factory for producing the higher-mass stellar black hole mergers that gravitational wave observatories have increasingly detected. The strange part about black hole sizes taken together is how much the universe seems to prefer extremes and struggle with the middle. Enormous supermassive giants at galactic centers, comparatively modest stellar remnants scattered throughout galaxies, and a genuinely uncertain, still being mapped population somewhere in between. A reminder that even after more than a century of theoretical work, we are still filling in fairly basic details about how common each type of black hole actually is, and exactly how each size category came to exist in the first place. A considerably more speculative and, for a period, genuinely controversial category of hypothetical black hole involves objects far smaller than anything discussed so far, Microscopic black holes theorized to potentially form during high-energy particle collisions, an idea connected to certain proposed extensions of physics involving extraspatial dimensions beyond the three we experience directly. When the Large Hadron Collider at CERN began operating in 2008, a small number of individuals raised public concern that particle collisions at the collider's unprecedented energies might create a microscopic black hole capable of growing and eventually consuming the Earth. Concerns serious enough that CERN's own physicists published a formal safety review directly addressing the possibility. That review concluded the scenario was not physically plausible for two independent and mutually reinforcing reasons. First, even if such microscopic black holes could form, Hawking radiation, discussed at length later in tonight's video, predicts they would evaporate away in a small fraction of a second, far too quickly to grow or consume any surrounding matter at all. And second, cosmic rays with energies vastly exceeding anything the Large Hadron Collider can produce have been striking Earth's atmosphere and other astronomical bodies continuously for billions of years without any observed catastrophic consequence, providing a genuinely reassuring natural experiment already run and already safely completed, long before the collider itself was ever built. No microscopic black hole of any kind has ever been detected at the Large Hadron Collider or anywhere else, and the entire concept remains a theoretical possibility connected to extra-dimensional physics that itself remains unconfirmed, rather than an established phenomenon of any kind. Stellar collapse also predicts a second, considerably higher mass gap, sitting at the opposite end of the stellar mass black hole range from the one discussed earlier in this chapter. Stellar evolution theory predicts that black holes formed directly from a dying star's core collapse should not exist within a specific mass window, roughly 65 to 130 times the mass of the Sun, since stars massive enough to leave behind a remnant in that specific range are expected, according to standard models, to instead be almost completely destroyed in an especially violent category of supernova called a pair instability supernova, in which the core becomes hot and dense enough to spontaneously convert gamma-ray energy into matter-antimatter particle pairs, triggering a runaway explosion that blows the entire star apart and leaves no black hole remnant at all. When LIGO and Virgo detected a black hole merger in May 2019, cataloged as GW190521, producing a resulting black hole of roughly 142 solar masses, the individual black holes involved in that specific merger fell partly within this theoretically forbidden mass window, a genuine tension between observation and stellar theory that researchers have proposed resolving through hierarchical mergers. The idea that these particular black holes may themselves already be the products of earlier black hole mergers, inheriting mass no single star's direct collapse could have produced, rather than having formed through the direct collapse of one massive star alone, a hypothesis that remains actively debated rather than fully confirmed. There's a second, considerably more specific gap worth mentioning, sitting right at the boundary between the heaviest known neutron stars and the lightest known black holes. Conventional stellar physics predicted a fairly clean dividing line here. The most massive neutron stars top out around 2.2 times the mass of our Sun before collapsing further, while the lightest confirmed black holes rarely fall below roughly 5 solar masses, leaving the range in between looking, for decades, essentially empty in every catalog astronomers had assembled through traditional telescope observations. Gravitational wave detectors complicated that clean picture directly when LIGO and Virgo detected a merger on August 14, 2019, cataloged as GW190811 involving a black hole of about 23 solar masses merging with a considerably smaller companion of roughly 2.6 solar masses, an object landing squarely inside the supposedly empty gap. To this day, no instrument has been able to determine with full confidence whether that smaller object was the lightest black hole ever measured or the heaviest neutron star ever measured, a genuine either-or ambiguity that has prompted renewed theoretical work on precisely how dense ordinary neutron star matter can become before it's forced to collapse the rest of the way into a black hole, a question this single, stubbornly ambiguous merger event has kept genuinely open. A separate and genuinely significant discovery, published independently by two research teams led by astronomers Carl Gebhardt and Laura Ferraris in the year 2000, revealed that a supermassive black hole's mass correlates remarkably tightly with an entirely separate, seemingly unrelated property of its host galaxy: the average velocity at which stars orbit and move within the galaxy's central bulge, a quantity astronomers call velocity dispersion. This relationship, now known as the M-sigma relation, holds with a genuinely surprising degree of precision across galaxies of vastly different total sizes and total star counts, suggesting some kind of physical connection, still not fully understood, between the growth of a central supermassive black hole and the broader formation and evolution of its entire host galaxy, even though the black hole itself, even at its largest, typically makes up only a tiny fraction of a percent of the galaxy's total mass and gravitationally influences only a comparatively small region immediately around the galactic center. Several competing explanations have been proposed for why this correlation exists at all, most centered on the idea that periods of active feeding, of the kind that power the quasars discussed later in tonight's video, release enough energy back into the surrounding galaxy to regulate and limit further star formation and gas inflow, creating a self-regulating, once-upon, feedback loop that ties the black hole's own growth to the galaxy's growth more broadly, though the precise physical mechanism responsible for enforcing this tight correlation across such a wide range of galaxy types remains an active and genuinely unresolved subject of research in galactic astrophysics. At the exact center of the Milky Way, roughly 26,000 light-years from Earth in the direction of the constellation Sagittarius, sits a supermassive black hole named Sagittarius A, pronounced Sagittarius A star. Its existence was inferred long before it was directly imaged through one of the more patient observational campaigns in the history of astronomy. Beginning in the early 1990s, teams led by astronomers including Andra Ghez and Reinhard Genzel began tracking the orbits of individual stars near the galactic center using increasingly sophisticated infrared telescopes capable of seeing through the thick clouds of dust that block visible light along that line of sight. What they found was remarkable. A star catalogued as S2, orbiting the galactic center on a tight, highly elliptical path, completes a full orbit in just over 16 years, remarkably fast for an orbit of that scale, comparable to how quickly Mercury circles our Sun despite S2's orbit being vastly larger in absolute terms. By carefully tracking S2's exact position over multiple full orbits and applying the same orbital mechanics Newton and Kepler developed for planets, Gez's and Genzel's teams calculated that whatever S2 was orbiting had to have a mass of roughly 4 million times that of our Sun, compressed into a region smaller than our solar system. No known astronomical object other than a black hole could explain gravity that strong, concentrated in a space that small. Work that earned Ghez and Genzel a share of the 2020 Nobel Prize in Physics, alongside Roger Penrose, who had earlier proven mathematically that black hole formation was an inevitable consequence of general relativity under realistic conditions, rather than a special case mathematical curiosity. Sagittarius A is, by supermassive black hole standards, relatively quiet and modest. Its estimated mass of roughly 4 million solar masses is genuinely small compared to some supermassive black holes discovered elsewhere in the universe, some of which exceed 10 billion solar masses. It's also not actively feeding on large quantities of surrounding material the way some galactic centers are, which is part of why it took infrared and radio observations rather than the bright X-ray signatures produced by actively feeding black holes, like Cygnus X1, to confirm its presence and characteristics. The stars orbiting closest to Sagittarius A travel at genuinely extraordinary speeds. S2, at its closest approach, moves at roughly 3% of the speed of light, fast enough that Einstein's general relativity produces measurable effects on its orbit that simple Newtonian mechanics alone would miss, effects including a gradual rotation of the orbit's orientation over successive passes, called relativistic precession, which was directly measured for the first time in observations, published in 2020, providing yet another confirmation that general relativity's predictions hold up even in this extreme gravitational environment. It's worth being precise about what all of this evidence actually establishes and what remains inferred rather than directly observed. The orbital measurements of stars like S2 tell us with very high confidence that an enormous, compact, invisible mass sits at the galactic center. What they cannot do on their own is prove that mass has an event horizon in the specific sense general relativity predicts, rather than being some other, even more exotic and currently unknown type of ultra-compact object. That gap between overwhelming indirect evidence and a direct confirmation of an event horizon specifically is exactly what the next chapter's breakthrough was designed to close. Sagittarius A also anchors an enormous complex ecosystem of gas, dust, and stellar remnants, collectively known as the galactic center region, including dense star clusters, filaments of magnetized gas, and the occasional flare of increased brightness in X-ray and infrared light, believed to result from small clumps of gas or dust falling across the event horizon and heating dramatically in their final moments. Some of these flares have been observed brightening by a factor of 100 or more within the span of just a few hours, offering astronomers rare, direct glimpses of individual accretion events happening in something close to real time, roughly 26,000 years after they actually occurred, given the light's long journey to reach us. One especially anticipated close encounter, involving an object called G2, gave astronomers a genuine real-time test of exactly how Sagittarius A would respond to a meaningful meal passing dangerously close. First identified in 2011 by a research team including astronomer Stephen Gillison, G2 was initially interpreted as a dense, compact cloud of gas roughly 3 times the mass of Earth, on a trajectory that would bring it within a mere few dozen billion kilometers of the black hole's event horizon in 2014, close enough that many astronomers anticipated a dramatic, highly visible feeding event, complete with a significant brightening in X-rays, as the cloud's material was torn apart and consumed. When 2014 arrived, G2 survived its closest approach essentially intact, showing only modest tidal distortion and no corresponding outburst in Sagittarius, as brightness, a genuinely surprising non-event that led most researchers studying it to revise their original interpretation, concluding G2 was more likely a compact star wrapped in its own shroud of gas and dust, dense and gravitationally bound enough to survive the black hole's tidal forces relatively unscathed, rather than a loose, easily disrupted gas cloud. As first assumed, a specific example of how even a single well-monitored close approach can end up testing and revising astronomers' basic assumptions about what they're actually observing. A further significant advance came in 2024 when the Event Horizon Telescope collaboration released a new polarized light image of Sagittarius, a building directly on the original 2022 image discussed later in tonight's video, revealing the specific structure of the magnetic field immediately surrounding the black hole's glowing ring for the first time. The polarization pattern, which traces how the magnetic field is oriented as light spirals through the superheated gas near the event horizon, showed a structure strikingly similar to the magnetic field pattern already documented around M87. Despite the two black holes differing enormously in mass and feeding rate, a similarity researchers have proposed suggests strong, ordered magnetic fields may be a common and fundamental feature of the material immediately surrounding black holes generally, rather than something unique to unusually large or unusually active systems, though confirming that pattern holds true across a wider population of black holes remains an active goal for the Event Horizon Telescope's continuing observation campaigns. The star S2, already introduced earlier in this chapter for its precisely measured orbital precession, provided astronomers with a second, independent confirmation of general relativity in 2018, when it made its closest approach to Sagittarius A in its roughly 16-year orbit, passing within about 120 astronomical units of the black hole at nearly 3% of the speed of light. A European collaboration operating an instrument called Gravity, mounted on the Very Large Telescope in Chile, measured a subtle shift in the specific wavelength of light arriving from S2 during that closest approach, called gravitational redshift, in which light climbing out of a strong gravitational field loses energy and shifts toward longer, redder wavelengths, an effect general relativity predicts but that simple Newtonian gravity does not. The Gravity collaboration's 2018 measurement matched Einstein's predicted redshift value closely enough to further rule out several proposed alternative theories of gravity that had been constructed specifically to avoid requiring dark matter or dark energy, since those alternative theories generally predict a measurably different redshift value under these exact extreme conditions. Because S2 completes a full orbit only once every 16 years, astronomers had to wait through an entire additional orbital cycle after earlier, less precise instrumentation first attempted similar measurements, meaning the 2018 result represented the first time. This specific relativistic effect could be measured with sufficient precision near a supermassive black hole specifically, rather than in the comparatively gentler gravitational environments like the Sun's own gravity or Earth's, where gravitational redshift had already been confirmed decades earlier. S2 is far from the only closely orbiting star astronomers track near Sagittarius, and improved infrared instrumentation has continued identifying stars on even tighter, faster orbits since S2's own discovery. A star catalogued as S4711, identified through continued monitoring by the same general research groups responsible for S2's original tracking, and reported in 2020, was found to complete a full orbit around the galactic center in just over 7 years, considerably faster than S2's roughly 16-year period, reaching an estimated top speed of about 8% of the speed of light at its closest approach, making it, at the time of its discovery, the fastest orbiting star ever confirmed anywhere in the galaxy. A separate star, S62, discovered through similar methods and reported the same year, showed an even tighter orbital period of under 20 years, despite passing remarkably close to the black hole at its own closest approach. And researchers studying this small but growing population of extreme close-orbiting stars, informally nicknamed the S-cluster, continue searching for still faster, still closer orbiting stars specifically, because each new discovery offers another independent opportunity to test general relativity's predictions under increasingly extreme conditions, squeezing ever more precise constraints on Sagittarius A, exact mass, and on any possible deviation from Einstein's equations that a sufficiently close, sufficiently fast stellar orbit might eventually reveal. For most of the history of black hole science, seeing one meant inferring its presence indirectly, from the orbits of nearby stars, from X-rays emitted by superheated infalling gas, from the gravitational tug on a visible companion. On April 10, 2019, that changed, an international collaboration called the Event Horizon Telescope released the first ever direct image of a black hole's shadow. Not Sagittarius A, but a far more massive black hole at the center of a galaxy called Messier 87, roughly 55 million light-years away, in the constellation Virgo. The technical achievement behind that image is worth understanding in some detail because it explains why it took so long to accomplish. A single telescope, no matter how large, doesn't have anywhere close to the resolving power needed to image an object as small, in apparent angular size, as a black hole's event horizon at that distance. Astronomers have compared the challenge to trying to photograph an object the size of an orange on the surface of the Moon, using a telescope on Earth. The Event Horizon Telescope solved this using a technique called very long baseline interferometry, linking together 8 radio telescopes spread across the globe, from Hawaii to the South Pole to Spain, and using precise atomic clocks to synchronize their observations so precisely that the entire network effectively has a single telescope roughly the size of Earth. ALF. The M87 black hole, cataloged as M87, is estimated at approximately 6.5 billion solar masses, one of the most massive black holes ever measured, and its enormous size, ironically, made it a somewhat easier imaging target than our own galaxy's comparatively modest Sagittarius A, because a more massive black hole has a proportionally larger event horizon, even though M87 is vastly farther away. The resulting image showed exactly what general relativity had predicted decades earlier. A dark central shadow, roughly 2.5 times larger than the black hole's actual event horizon due to the extreme bending of light around it, surrounded by a bright, asymmetric ring of superheated glowing gas. That asymmetry in the ring's brightness wasn't a flaw or an artifact. It was itself a confirmed prediction caused by relativistic beaming, the effect by which gas moving toward an observer at a significant fraction of the speed of light appears brighter than gas moving away, allowing astronomers to determine the black hole is rotating and even estimate the direction of that rotation relative to Earth. In 2022, the same collaboration released a second landmark image, Sagittarius A itself, our own galaxy's central black hole, imaged directly for the first time. This posed an even harder technical challenge than M87, because Sagittarius A, much smaller size, means the gas swirling around it completes a full orbit in a matter of minutes, rather than the days or weeks it takes around the far larger M87, meaning the image could blur within the observation window itself, requiring new computational techniques developed specifically to account for that rapid variability. The resulting image showed a strikingly similar dark shadow surrounded by a glowing ring, remarkable confirmation that 2 black holes differing in mass by a factor of more than 1,000, one relatively calm and modest, one enormous and among the largest ever measured, both produce shadows consistent with the same underlying physics. It's worth being honest about exactly what these images do and don't show. What we're seeing is not the black hole itself. Nothing about the event horizon or the interior can ever be directly photographed by definition, since no light escapes from within it to form an image. What the Event Horizon Telescope actually captured was the silhouette the black hole casts against the glowing, superheated gas immediately surrounding it. The shadow shaped precisely by the extreme gravitational bending of light general relativity predicts. It's an image of the black hole's effect on its surroundings, rendered with such precision that it matches theoretical predictions almost exactly. Arguably, one of the most direct confirmations of general relativity's most extreme predictions ever obtained, achieved not with a single telescope, but with an entire planet pressed into service as one. The sheer logistics behind actually producing that first 2019 image involved a genuinely striking, distinctly unglamorous engineering problem: data volume. Each of the Event Horizon Telescope's 8 observing sites recorded such an enormous volume of raw radio data. During the project's dedicated observing campaign, several petabytes in total across the entire array, that transmitting it over the internet, even using the fastest research networking connections available at the time, would have taken an entirely impractical amount of time. Instead, the collaboration physically recorded the data onto stacks of specialized hard drives at each individual telescope site and shipped them by conventional air freight to two central data processing centers, one at MIT's Haystack Observatory in Massachusetts and one at the Max Planck Institute for Radio Astronomy in Germany, where the recordings from every site were finally combined and cross-referenced. This physical shipping process introduced its own genuinely unusual delay. The South Pole Telescope, one of the array's 8 sites, could only have its hard drives flown out during the brief Antarctic summer season, since aircraft cannot safely reach the South Pole Station for months at a time. Otherwise, meaning the South Pole's contribution to the final image sat waiting in storage for several months after the actual 2017 observing run before it could even begin being combined with data from the other 7 sites. A genuinely old-fashioned physical bottleneck sitting at the very center of one of the most technologically sophisticated scientific achievements of the 21st century. Turning that combined, physically reassembled data into an actual viewable image required solving a genuinely difficult computational problem of its own, since the 8-telescope array, however cleverly synchronized, still only sampled a limited, irregularly spaced set of measurement points across the effective Earth-sized telescope it was simulating, leaving considerable gaps in the raw data that had to be carefully and honestly filled in through image reconstruction algorithms rather than direct, complete observation. Computer scientist Katie Booman, then a graduate student at MIT, led development of one of several independent algorithms used for this reconstruction process called Copper-Carp, and the Event Horizon Telescope collaboration deliberately organized itself into multiple, separate teams, each working with different reconstruction algorithms and deliberately avoiding communication with each other during the analysis, specifically so that if every team's independently generated image converged on a similar-looking result, the collaboration could be confident the final image reflected genuine structure in the data itself rather than any single team's particular software choices or unconscious assumptions accidentally shaping the outcome. A widely circulated photograph of Booman reacting with visible excitement as the first successful reconstructed image of M87 appeared on her laptop screen became one of the more publicly recognizable human moments connected to the entire project, spreading rapidly across social media. Following the image's official 2019 release, even as Booman herself and her Event Horizon Telescope colleagues have consistently and publicly emphasized that the achievement reflected the coordinated work of more than 200 researchers across the collaboration, rather than any single algorithm or individual scientist. The 2019 and 2022 images represent only the beginning of the Event Horizon Telescope's ambitions, and a planned expansion called the Next Generation Event Horizon Telescope, or NGEHT, currently in active development with additional planned observing stations across several continents, aims to roughly double the number of participating telescopes and add considerably improved sensitivity at multiple radio frequencies simultaneously, rather than the single frequency the original 2019 observation campaign relied on. Astronomers involved in the NGEHT project have specifically proposed that the improved array should be capable of producing genuine video, rather than a single static image, of gas actually orbiting and swirling around a black hole's photon sphere in close to real time, a goal that would allow direct observation of individual hot spots of gas completing their orbits, providing a genuinely dynamic test of general relativity's predictions rather than the single still-frame snapshots obtained so far. Researchers have also proposed extending the array with a radio telescope in space, since removing the atmospheric interference and vastly increasing the effective telescope size by placing a receiver in orbit would allow imaging black holes with even higher resolution than any purely ground-based array, however large, could ever achieve, though such a space-based addition remains, as of the most recent published mission planning, a longer-term proposal rather than a funded and scheduled project. One of the most commonly asked questions about black holes is also one of the strangest to actually answer honestly, because the answer depends entirely on who is doing the asking and from where. Physicists distinguish carefully between what an observer falling into a black hole would experience and what a distant observer watching them fall would see. And remarkably, according to general relativity, these two perspectives don't agree with each other at all. Let's start with the falling observer. As you approach a black hole, the difference in gravitational pull between the part of your body closest to the black hole and the part farthest away, a difference called tidal force, grows steadily stronger. For a supermassive black hole like Sagittarius A or M87, this tidal stretching near the event horizon is actually relatively gentle because the event horizon itself is so large that the gravitational gradient across the length of a human body remains manageable. Some physicists have calculated you could cross the event horizon of a sufficiently massive black hole without immediately noticing anything unusual at all. For a much smaller stellar mass black hole, however, the story is dramatically different and far more violent, because the event horizon is much closer to the extreme gravity of the singularity. Well before reaching the horizon of a stellar mass black hole, tidal forces would stretch a falling body lengthwise while compressing it sideways, a process astrophysicists have somewhat memorably nicknamed Spaghettification, first popularized in this specific term by physicist Stephen Hawking in his writing for general audiences. The more genuinely mind-bending part of this story involves what a distant observer, watching someone fall toward a black hole from a safe distance, would actually see. According to general relativity, gravity doesn't just bend space, it also affects the flow of time itself, a phenomenon called gravitational time dilation, and it grows more extreme the closer you get to an event horizon. From the distant observer's perspective, the falling person would appear to move, increasingly slowly as they approached the horizon, their light growing dimmer and increasingly red-shifted, stretched toward longer and longer wavelengths, never actually appear to finish crossing the horizon at all from the outside observer's frame of reference, instead seeming to freeze, fade, and eventually become undetectably faint, approaching the horizon asymptotically, but never visibly completing the crossing. This creates a genuinely strange asymmetry that took physicists years to fully reconcile. The falling observer, from their own perspective, experiences nothing unusual at the horizon itself and crosses it in a perfectly ordinary, finite amount of their own personal time, according to their own clock, while the distant observer watching them never sees them actually finish the crossing at all. Both descriptions are considered correct within general relativity, simply describing the same physical event from two reference frames whose experience of time genuinely diverges near a black hole in ways ordinary intuition, built entirely from everyday non-extreme gravity, simply doesn't prepare you for. Once past the event horizon, which again involves no dramatic physical sensation at the boundary itself for the falling observer, according to the mathematics, every possible direction of travel, forward, backward, left, right, points only toward the central singularity, in the same sense that every direction on Earth's surface, once you're standing at the North Pole, points south. Continuing to fall becomes not a choice but simply the only direction time itself can move. According to general relativity's description of the interior geometry, until reaching the singularity, where, depending on which unresolved theoretical framework eventually turns out to correctly describe that region, The equations either predict genuine, infinite density destruction, or, according to some more speculative and unconfirmed proposals we'll touch on later, something considerably stranger. It's worth being clear that no human, being and no probe of any kind, has ever actually tested any of this directly, and given the physics involved, it's difficult to imagine how any information from inside an event horizon could ever be sent back out to confirm it, since nothing, including any conceivable radio signal, can escape once the boundary is crossed. Everything described in this chapter is a rigorously derived mathematical consequence of general relativity, a theory that has passed every experimental test thrown at it for over a century, applied to a set of conditions so extreme that direct verification, at least of the interior details, may simply never be possible even in principle. Not every black hole discussed across tonight's video sits neatly in a binary system with a visible companion star feeding it, and a small but genuinely significant population, formed from massive stars that simply never had a close companion at all, are believed to drift alone through interstellar space, gravitationally influencing nothing bright enough to reveal their presence through conventional means. Astronomers first confirmed the direct detection of one such isolated black hole in 2022 through a technique called gravitational microlensing, in which the black hole's own gravity briefly bends and magnifies the light of a more distant background star, as the black hole happens to pass almost precisely in front of it from Earth's perspective, producing a characteristic temporary brightening of the background star lasting weeks to months, with no light at all coming from the black hole itself. Two independent research teams analyzing years of accumulated data from the Hubble Space Telescope, tracking one such microlensing event first identified in 2011, reached slightly different mass estimates for the intervening object, with one team's analysis suggesting a mass consistent with an isolated stellar mass black hole roughly 7 times the Sun's mass, while the other proposed it might instead be an unusually massive neutron star, a genuine scientific disagreement that remains only partially resolved, and that illustrates just how difficult it remains to fully characterize an object detected purely through its gravitational effect on background starlight with no additional confirming evidence, such as X-ray emission or a visible companion, available to help settle the question more definitively. Just outside the event horizon itself, at a distance exactly 1.5 times the Schwarzschild radius for a non-rotating black hole, sits a genuinely strange region called the photon sphere, where gravity is strong enough to bend light into a perfect circular orbit around the black hole, chasing its own tail indefinitely, rather than either escaping outward or falling inward. The photon sphere is inherently unstable, meaning any photon actually placed there would eventually spiral either outward to freedom or inward across the horizon after enough orbits, given the slightest perturbation. But it produces a genuinely disorienting theoretical consequence worth sitting with directly, a hypothetical observer hovering safely just outside a black hole's photon sphere could, in principle, look directly ahead in any direction and see the back of their own head, since light emitted from behind them could loop entirely around the black hole, along the photon sphere before completing its circuit and arriving back at their own eyes. This same photon sphere is directly responsible for the glowing ring visible in the Event Horizon Telescope images discussed in the previous chapter, since the bright ring photographed around M87 and Sagittarius A is, physically, the accumulated light from superheated gas that happened to pass close enough to loop partway around the photon sphere before continuing on toward Earth, meaning the ring's specific size and shape function as a direct, physically observable signature of the photon sphere's exact location and geometry, a genuinely elegant connection between one of general relativity's stranger theoretical predictions and one of its most literal, photographable confirmations. The gravitational time dilation responsible for so much of this chapter's strangeness near a black hole isn't some exotic effect confined only to extreme gravity, and it was first confirmed experimentally not near any black hole at all, but inside a physics building at Harvard University. In 1959, physicists Robert Pound and Glenn Rebka conducted a now famous experiment measuring the tiny gravitational redshift of gamma rays, traveling just 22.5 meters up a tower on Harvard's campus, exploiting a newly discovered nuclear physics technique called the Nussbauer effect to achieve the extraordinary precision needed to detect a wavelength shift caused by a gravitational difference this genuinely small. Pound and Rebka's measurement confirmed Einstein's predicted gravitational redshift to within about 10%, an experiment considered, even today, one of the most elegant and important tabletop confirmations of general relativity ever performed, precisely because it demonstrated that gravity's effect on time isn't a special property unique to black holes or other extreme astrophysical objects, but a universal feature of gravity itself, present, if minutely and practically undetectable in most everyday circumstances, even across the modest height difference of a university physics building, scaling up from there by the same underlying physics into the far more dramatic time dilation this chapter has spent so much time describing near an actual event horizon. Everything discussed so far has largely described what physicists call a Schwarzschild black hole, a simplified, idealized case, perfectly spherical and entirely non-rotating. Real black holes, formed from collapsing stars that were themselves rotating, or from mergers between other rotating black holes, are expected to carry significant angular momentum, and a rotating black hole behaves in ways meaningfully different from its idealized, stationary cousin. The mathematics describing a rotating black hole were worked out in 1963 by New Zealand mathematician Roy Kerr, and black holes with spin are accordingly called Kerr black holes in his honor. Rotating black hole doesn't just spin in place the way a planet does. It actually drags the surrounding space-time itself around with it, a genuinely predicted effect called frame dragging, first proposed in a different context by physicist Josef Lense and Hans Thirring back in 1918, and later confirmed to occur in a far more modest form around Earth itself through a dedicated satellite experiment called Gravity Probe B, whose results, published in 2011, matched Einstein's predicted frame-dragging effect from our comparatively gentle rotating planet to within about 19% of the predicted value. A striking confirmation that this bizarre effect isn't unique to black holes, just enormously more pronounced around them. Around a rotating black hole, this frame-dragging effect creates a region called the Ergosphere, located just outside the event horizon itself, shaped something like a flattened, pumpkin-like sphere that touches the event horizon at the poles of rotation but bulges outward at the equator. Inside the ergosphere, space-time is being dragged around the black hole so forcefully that it becomes physically impossible for any object, regardless of how powerful its engines might theoretically be, to remain stationary relative to a distant observer. Everything within the ergosphere is compelled to orbit in the same direction the black hole spins, whether it wants to or not. Crucially, though, the ergosphere is not yet the point of no return. Objects can still, in principle, enter the ergosphere and later escape back out, unlike the event horizon itself. This unusual property of the ergosphere led physicist Roger Penrose to propose in 1969 a genuinely remarkable theoretical process for extracting energy from a rotating black hole. In what's now called the Penrose process, an object entering the ergosphere could, in principle, be split into two pieces, with one piece falling into the black hole on a carefully chosen trajectory, while the other piece is flung back out. And due to the specific mechanics of the ergosphere's frame dragging, the piece that escapes can carry away more energy than the entire original object possessed, with the difference coming directly from the black hole's own rotational energy, very slowly spinning it down over the course of the extraction. no one has ever built anything resembling a Penrose process extractor, and it remains purely theoretical from an engineering standpoint. But some physicists have speculated that sufficiently advanced civilizations could, in principle, use rotating black holes as genuinely practical, if extraordinarily ambitious, energy sources, an idea occasionally explored seriously in academic papers on advanced energy extraction, even while remaining firmly in the realm of theoretical speculation for the time being. Rotation also changes the geometry of the event horizon and singularity themselves in significant ways. A maximally rotating Kerr black hole has an event horizon that shrinks compared to a non-rotating black hole of the same mass, and instead of a single point, the singularity itself takes the mathematical form of a thin ring rather than a point, a detail that has led some theoretical physicists to speculate, in a genuinely unconfirmed and highly mathematical vein, we'll touch on again later, about whether a sufficiently precise trajectory through a rotating black hole's ring singularity might, according to certain solutions of the equations, avoid the singularity itself and connect to another region of space-time entirely. This remains firmly in the territory of mathematical possibility rather than established physics, and most physicists consider it unlikely to survive contact with a complete theory of quantum gravity. But it's a genuinely fascinating consequence of taking Kerr's 1963 equations seriously and following them to their logical extremes. Observationally, astronomers have found strong indirect evidence that many real black holes, both stellar mass and supermassive, are indeed spinning, in some cases quite rapidly, inferred from the way surrounding gas heats and emits X-rays as it spirals inward, with the specific patterns of that emission depending sensitively on how fast and in what direction the underlying black hole is rotating. Measurements that have, in a number of well-studied cases, suggested spin rates approaching a meaningful fraction of the theoretical maximum a black hole's geometry can support. One particularly well-studied example, a stellar mass black hole, roughly 10 to 18 times the mass of the Sun, catalogued as GRS 1915-105, located within our own galaxy, became one of the first black holes for which astronomers attempted a direct spin measurement through research published beginning in 2006 by a team led by astrophysicist Jeffrey McClintock, analyzing the specific temperature and brightness profile of X-rays emitted by its accretion disk. Their analysis suggested GRS 1915+105 was spinning at close to the theoretical maximum rate a black hole's geometry can physically support, a limit beyond which the mathematics of a Kerr black hole predicts the event horizon itself would disappear entirely, exposing a naked singularity of exactly the kind Roger Penrose's cosmic censorship hypothesis, discussed later in tonight's video, proposes nature always prevents. Subsequent reanalyses using an independently developed measurement technique based on modeling the relativistic broadening of a specific iron emission line in the black hole's X-ray spectrum rather than its overall disk temperature have produced somewhat different spin estimates for the same object, a discrepancy that has become a genuinely useful, actively studied case study in just how difficult it remains to precisely measure a black hole's rotation rate from a distance, since the two competing measurement methods rely on different assumptions about the accretion disk's geometry and can, in certain systems, disagree meaningfully with each other, even when applied to identical underlying X-ray data. A rotating black hole's stored energy isn't merely a theoretical curiosity extractable only through the purely hypothetical Penrose process described earlier in this chapter, and astrophysicists generally believe a closely related, considerably more astrophysically realistic mechanism, called the Blandford-Znajek process, is directly responsible for powering the enormous relativistic jets observed streaming from many active black holes, including the quasar jets discussed later in tonight's video. First proposed in a 1977 paper by physicists Roger Blandford and Roman Znajek, The process describes how a rotating black hole's frame-dragging effect can twist and wind up magnetic field lines, threading through the surrounding accretion disk and ergosphere, converting a portion of the black hole's own rotational energy directly into the electromagnetic energy needed to accelerate charged particles to velocities approaching the speed of light, launching them outward along the black hole's rotational axis in the two narrow, tightly collimated jets visible in radio and X-ray observations of countless active galaxies. Unlike the Penrose process, which remains purely theoretical and has never been connected to any observed astrophysical phenomenon, the Blandford-Znajek mechanism is now generally considered by astrophysicists to be strongly supported by observational evidence, including direct measurements suggesting jet power correlates with estimated black hole spin in several well-studied systems, making it one of the more observationally grounded applications of the same basic rotational energy extraction physics Penrose first proposed on purely theoretical grounds nearly a decade earlier. There's a theoretical speed limit built directly into the mathematics of a rotating Kerr black hole worth mentioning here, closely connected to the black hole thermodynamics discussed later in tonight's video. A black hole cannot spin arbitrarily fast for a given mass. Beyond a specific maximum rotation rate, the equations predict the event horizon itself would vanish entirely, exposing the singularity directly to the outside universe as the naked singularity. Roger Penrose's cosmic censorship hypothesis proposes nature always forbids. A black hole spinning at exactly this theoretical maximum is called an extremal black hole, and physicists studying black hole thermodynamics have found that an extremal black hole's temperature, in the same Bekenstein-Hawking sense discussed in a later chapter, would drop to absolute zero, unable to emit any further Hawking radiation at all, a result closely paralleling the third law of ordinary thermodynamics, which states that no physical process can ever actually bring an object's temperature down to absolute zero in a finite number of steps. In this specific analogy, continuously spinning a black hole up toward its theoretical maximum rotation rate behaves mathematically like continuously cooling an ordinary system toward absolute zero, approaching the limit asymptotically, but, according to the same thermodynamic reasoning, never actually and completely reaching it, meaning no confirmed astrophysical black hole is believed to spin at the precise, exact extremal limit itself, even though several well-studied candidates, including GRS 1915-105 discussed earlier in this chapter, have been measured spinning remarkably close to it. On September 14, 2015, two identical detectors, one in Louisiana and one in Washington State, both part of a collaboration called LIGO, the Laser Interferometer Gravitational Wave Observatory, recorded an almost identical, extraordinarily faint signal within milliseconds of each other. After months of careful analysis to rule out instrumental error or terrestrial interference, the collaboration announced in February 2016 that they had made the first direct detection in history of gravitational waves. Ripples in the fabric of spacetime itself, predicted by Einstein a full century earlier, in 1916, but never before directly observed because the effect is almost unimaginably faint by the time it reaches Earth from its source. The signal, now known by its detection date as GW150914, was traced to the collision and merger of two black holes located roughly 1.3 billion light-years away, with masses of approximately 36 and 29 times that of our Sun. As the two black holes spiraled toward each other in their final moments before merging, they generated ripples in space-time that spread outward in all directions at the speed of light, carrying away an almost unimaginable amount of energy. The peak power, radiated during the final fraction of a second of the merger, calculated from the signal's characteristics, briefly exceeded the combined light output of every star in the observable universe put together, even though almost none of that energy was released as light at all. but as pure gravitational radiation. The way LIGO actually detects these signals is worth explaining, because the sensitivity involved is genuinely difficult to comprehend. Each LIGO detector consists of two perpendicular tunnels, each 4 kilometers long, with laser beams bounced back and forth between precisely positioned mirrors at each end. A passing gravitational wave stretches space in one direction while compressing it in the perpendicular direction, changing the relative length of the two tunnels by an amount so small that LIGO researchers have described the detector's sensitivity as being capable of measuring a change in distance a 1,000 times smaller than the width of a single proton across the entire 4-kilometer length of the tunnel. A level of precision that required inventing entirely new categories of vibration isolation, vacuum technology, and laser stabilization to achieve. The discovery earned physicists Rainer Weiss, Barry Barish, and Kip Thorne, the same Kip Thorne who had wagered with Stephen Hawking decades earlier over Cygnus X1's existence, the 2017 Nobel Prize in Physics, and it opened an entirely new observational window on the universe, one that doesn't rely on light or any form of electromagnetic radiation at all. In the years since that first detection, LIGO, joined by additional detectors including Virgo in Italy and Kagra in Japan, has recorded dozens of additional black hole merger events, along with, in 2017, the first confirmed detection of a neutron star merger, an event that was also observed simultaneously across multiple wavelengths of light, definitively confirming that such mergers are a significant source of heavy elements, including gold and platinum, scattered throughout the universe. Gravitational wave astronomy has already begun reshaping some of the questions we covered earlier in this video. The masses of black holes detected through mergers have, in several cases, been surprisingly large for stellar mass objects, suggesting our understanding of exactly how massive a black hole can grow through. Stellar collapse alone may need revision, and some detected merger events have produced resulting black holes that fall squarely within the long elusive, intermediate mass range discussed in Chapter 3, offering some of the strongest direct evidence yet that this category genuinely exists in nature rather than being merely a theoretical gap. The strange part of gravitational wave astronomy, when you sit with it, is what it reveals about how thoroughly black hole collisions were happening throughout cosmic history, entirely undetected until 2015. These events don't produce light in any conventional sense. Two black holes, merging in the depths of space, releasing more energy in a fraction of a second than every star in the visible universe combined. And for the first 100 years after Einstein predicted the ripples such an event would send outward, humanity had no way of detecting even one of them, despite them apparently happening with some regularity throughout the observable universe, silently, until we finally built an instrument sensitive enough to notice space-time itself trembling as the wave passed through Earth. The final fraction of a second of a black hole merger signal, called the ring-down, offers physicists a direct and genuinely elegant way to test the no-hair theorem discussed earlier in tonight's video. Immediately after two black holes merge, the newly formed single black hole briefly rings like a struck bell, vibrating through a specific pattern of decaying oscillations called quasi-normal modes before settling into its final, smooth, stationary shape. And general relativity makes an extremely precise prediction about exactly what frequencies and decay rates those vibrations should have, based entirely on the resulting black hole's final mass and spin, and nothing else, because the no-hair theorem insists a black hole's properties are fully described by just those two numbers, once its charge is set aside as generally negligible for astrophysical objects, any rings and signal that didn't match the specific frequencies. General relativity predicts for that particular mass and spin would represent direct evidence that black holes carry some additional hidden property, or that general relativity itself breaks down under these extreme conditions. Analysis of the clearest ring-down signals LIGO and Virgo have detected, published across multiple studies since 2019, has so far found the observed vibration patterns consistent with general relativity's predictions to within the currently achievable measurement precision, offering some of the most direct evidence available that newly merged black holes really do settle down into the remarkably simple objects the mathematics describes, even as physicists continue refining detector sensitivity specifically to search for any subtle deviation that might finally point toward physics beyond Einstein's equations. A separate and more recent gravitational wave milestone involves signals far too slow and too faint for LIGO's kilometer-scale detectors to ever register directly. In 2023, several international collaborations, including the Nanograv Consortium in North America, published strong evidence for a faint, continuous gravitational wave background, permeating all of space, detected not through a laser interferometer, but through more than 15 years of extraordinarily precise timing observations of pulsars, rapidly spinning neutron stars whose radio pulses arrive with such clockwork regularity that tiny, correlated timing irregularities across dozens of widely separated pulsars can reveal gravitational waves passing through the entire galaxy. This background hum is believed to originate from the combined gravitational radiation of countless supermassive black hole binary pairs, slowly spiraling toward each other across galaxy mergers throughout cosmic history, too numerous and too overlapping in frequency for any single merger event to be picked out individually, meaning astronomers are, in effect, listening not to one black hole collision but to the collective, overlapping murmur of an untold number of them, happening continuously across the observable universe, a genuinely different, complementary way of listening to black holes than the individual, sharply defined chirps LIGO detects from nearby stellar mass mergers. The next generation of ground-based gravitational wave detectors, currently in active planning, aims to push sensitivity roughly tenfold beyond LIGO's current capability, a scale of improvement that would allow astronomers to detect essentially every black hole merger occurring anywhere in the observable universe, rather than the comparatively nearby, present-day sample current detectors are limited to. The Einstein telescope, a proposed underground European facility, arranged in a triangular configuration with detector arms 10 kilometers long, and Cosmic Explorer, a proposed American successor with arms stretching 40 kilometers, both remain in early planning and site selection stages as of the most recent published project updates, with construction not expected to begin before the early 2030s. Astronomers anticipate that this next generation of detectors would extend gravitational wave observations back to redshifts corresponding to the universe's very earliest generations of stars, potentially allowing direct observation of the first black hole mergers to have ever occurred, a genuinely significant expansion beyond the comparatively recent cosmic history LIGO and Virgo currently sample, and one that could finally offer a direct merger-by-merger accounting of black hole formation across essentially the entire history of the universe, rather than the necessarily incomplete present-day snapshot available from gravitational wave astronomy's first decade. Ground-based detectors like LIGO, however sensitive, are physically limited in the specific range of gravitational wave frequencies they can detect, since longer detector arms are needed to sense lower-frequency waves, and Earth's own size places a practical ceiling on how large any ground-based instrument could ever be built. The European Space Agency's Laser Interferometer Space Antenna, known as LISA, and currently scheduled for launch in the mid-2030s, addresses this limitation by placing 3 spacecraft in a triangular formation trailing Earth's orbit around the Sun, separated by roughly 2.5 million kilometers each, forming a gravitational wave detector vastly larger than anything achievable on Earth's surface and specifically sensitive to the lower-frequency gravitational waves produced by the supermassive black hole. Mergers discussed elsewhere in tonight's video, events LISA's space-based design would allow astronomers to observe directly and individually, rather than only inferring their combined overlapping presence through the pulsar timing background methods discussed earlier in this chapter. LISA is also expected to detect a genuinely different category of source entirely: smaller stellar mass black holes and neutron stars gradually spiraling into supermassive black holes over months or years, called extreme mass ratio inspirals, events that would allow astronomers to map the detailed space-time geometry immediately surrounding a supermassive black hole with a level of precision no other observational method could match, effectively using each infalling smaller object as an extraordinarily sensitive natural probe of the larger black hole's gravity. Still, as of tonight's most recent information, roughly a decade away from its first actual observations. For most of the 20th century, physicists treated black holes as objects that could only grow, absorbing matter and energy, but never releasing anything at all. A one-way street, entirely consistent with the classical picture of general relativity, in which nothing can escape from beyond the event horizon under any circumstances. That picture changed in 1974, when Stephen Hawking, applying the principles of quantum mechanics to the region immediately surrounding a black hole's event horizon, arrived at a genuinely startling theoretical conclusion. Black holes should, in fact, slowly emit radiation and lose mass over time, eventually evaporating away entirely. Given enough time, the mechanism behind what's now called Hawking radiation involves a genuinely strange feature of quantum field theory. According to quantum mechanics, empty space is never perfectly empty, but constantly produces and reabsorbs pairs of virtual particles and antiparticles, popping briefly into existence before annihilating each other so quickly that they don't violate any conservation laws. Hawking's insight was that near a black hole's event horizon, this process can be disrupted in a specific way. If one particle of such a pair falls across the horizon while its partner escapes outward, the escaping particle becomes real rather than virtual, effectively carrying away a small amount of energy that, by the strict accounting of energy conservation, must be subtracted from the black hole's own mass. Over immense timescales, this slow, steady leak of particles and energy causes the black hole to gradually shrink. The rate of this evaporation, according to Hawking's calculations, depends critically on the black hole's mass, and in a genuinely counterintuitive way, smaller black holes evaporate much faster than larger ones, because Hawking radiation grows more intense as an event horizon shrinks. For a stellar mass black hole, the timescale involved is almost incomprehensibly long. Current calculations suggest it would take roughly 10 to the power of 67 years for a black hole with the mass of our Sun to fully evaporate a number so large. It dwarfs the current age of the universe, roughly 13.8 billion years, by a margin that's difficult to express in any intuitive way. For the supermassive black holes at the centers of galaxies, the timescale stretches even further into numbers that exist essentially only as an abstract mathematical exercise, given how far they lie beyond any timescale relevant to the universe as currently observed. Where Hawking radiation becomes potentially relevant on more observable timescales is at the small end of the mass spectrum. A genuinely tiny black hole, hypothetically formed, for instance, from the primordial density fluctuations discussed in Chapter 3, with a mass comparable to a mountain or smaller, would, according to the same calculations, evaporate far more rapidly, and a sufficiently small primordial black hole could, in principle, be evaporating away right now, or could even have already fully evaporated in a final, theoretically dramatic burst of energy at the very end of its life, as the black hole shrinks towards zero mass and its Hawking radiation output increases correspondingly. No such evaporation event has ever been confirmed to astronomers. Despite searches for the specific gamma-ray signature such a final burst would theoretically produce, which is itself one of the pieces of observational evidence constraining just how common sufficiently small primordial black holes can actually be. It's worth being honest about the current status of Hawking radiation as a scientific idea. Despite being one of the most celebrated and widely accepted theoretical predictions in modern physics, Hawking radiation has never been directly observed from an actual astrophysical black hole, precisely because the predicted radiation from any realistically sized black hole is so extraordinarily faint that it remains utterly undetectable against the background radiation of the universe, using any instrument currently available or plausibly buildable with existing technology. What has been observed in laboratory settings are carefully constructed analog systems using flowing fluids or specially engineered arrangements of ultracold atoms designed to mathematically mimic certain properties of an event horizon that have shown effects consistent with a Hawking radiation-like process occurring in these artificial, non-gravitational analog systems, offering indirect but genuinely suggestive support for the underlying physics, even without a direct astrophysical detection. One of the most compelling of these analog experiments was conducted by physicist Jeff Steinhauer and colleagues at the Technion in Israel, using a carefully engineered cloud of ultracold atoms called a Bose-Einstein condensate, cooled to within a fraction of a degree of absolute zero, and manipulated so that a portion of the cloud flowed faster than the local speed of sound within the condensate itself, creating an acoustic analog of an event horizon. A boundary sound waves generated inside the faster-flowing region could never cross back out of, in direct analogy to how light cannot escape a gravitational event horizon. In a 2019 study published in Nature Physics, Steinhauer's team reported detecting pairs of correlated sound wave excitations, called phonons, emerging from this analog horizon in a statistical pattern matching Hawking's original theoretical prediction, closely enough that the team described it as the first experimental measurement of the specific quantum entanglement signature Hawking's calculation predicted should exist between the escaping radiation and its partner falling inward. Physicists studying analog gravity are careful to note that these experiments, however striking, test the same underlying quantum field theory applied to a sound wave horizon rather than an actual gravitational one, meaning they offer strong indirect support for the mathematics behind Hawking's reasoning without constituting direct proof that real astrophysical black holes emit radiation the same way, a distinction the researchers themselves have consistently and carefully emphasized, even while describing the result as a genuinely significant experimental achievement. Hawking radiation is closely connected to a related, and in some ways even stranger, theoretical prediction called the Unruh effect, first proposed by physicist Bill Unruh in 1976. Working independently of Hawking, but drawing on much of the same underlying quantum field theory. The Unruh effect predicts that an observer undergoing constant acceleration through completely empty space, far from any black hole, star, or gravitational field of any kind, should nonetheless perceive that seemingly empty space as being filled with a faint bath of thermal radiation at a temperature directly proportional to how strongly they're accelerating, while a second, non-accelerating observer occupying the exact same region of space would perceive nothing there at all. The effect arises because the very definition of a particle in quantum field theory turns out to depend on an observer's own reference frame and state of motion, meaning two observers, moving differently through identical empty space, can legitimately disagree about whether particles are present at all, a genuinely disorienting consequence that most physicists consider a close theoretical cousin of Hawking radiation, specifically because falling toward a black hole's event horizon and undergoing extreme acceleration in flat space turn out to be described by closely related mathematics. The Unruh effect has never been directly confirmed experimentally, since the acceleration required to produce a measurably significant temperature is extraordinarily large, far beyond what any current laboratory technology can sustain for a test particle, But several research groups have proposed increasingly creative potential experimental setups over the past decade, specifically designed to detect a diminished, indirect version of the effect, making it, alongside Hawking radiation itself, one of theoretical physics' most confidently derived predictions that still awaits its first direct laboratory confirmation. Popular visual culture actually got a rare, genuinely rigorous preview of what a black hole's gravitational lensing would truly look like well before the Event Horizon Telescope's own 2019 photograph, through an unlikely collaboration between theoretical physics and Hollywood filmmaking. For the 2014 film Interstellar, physicist Kip Thorne, the same Kip Thorne who wagered with Hawking over Cygnus X1, and later shared the 2017 Nobel Prize for LIGO's gravitational wave detection, worked directly with visual effects company Double Negative to render the film's fictional black hole, named Gargantua, using genuine general relativity equations rather than an artist's approximation or a simplified visual shortcut. The resulting rendering software, developed specifically for the production, and later described in a 2015 paper Thorne and the visual effects team, published in the peer-reviewed journal Classical and Quantum Gravity, actually uncovered a subtle rendering effect the team hadn't initially anticipated. Extremely fine, thread-like structures visible within the glowing accretion disk's image, caused by the same extreme gravitational lensing discussed throughout tonight's video, structures accurate enough to general relativity's actual predictions that the film's visual effects team was able to publish them as a genuine, if modest, contribution to the scientific literature on black hole visualization, a rare case of a major studio film's visual effects pipeline generating a peer-reviewed physics result as an unplanned byproduct of simply trying to make a fictional black hole look as scientifically accurate as possible. Hawking radiation's real significance lies less in astronomical observation and more in what it revealed theoretically. It was the first serious result to suggest that black holes obey a form of thermodynamics complete with a genuine temperature and an entropy value, connecting these previously separate objects, general relativity's black holes, and quantum mechanics, particle physics, in a way that hinted at a deeper unified theory neither framework could fully provide on its own. And that connection leads directly into one of the strangest and still genuinely unresolved puzzles in all of theoretical physics. Credit for first proposing that black holes might possess a genuine thermodynamic entropy actually belongs not to Hawking, but to physicist Jacob Bekenstein, then a graduate student, who argued in a 1972 paper that a black hole's entropy should be directly proportional to the surface area of its event horizon, a genuinely radical suggestion at the time, since it implied information and disorder scaled with an object's two-dimensional surface area rather than its three-dimensional volume, the way entropy behaves in essentially every other physical system ever studied. Hawking himself initially and publicly disagreed with Bekenstein's proposal, arguing that a black hole with genuine entropy and a genuine temperature would, by the basic laws of thermodynamics, have to radiate energy, which seemed to directly contradict general relativity's classical prediction that nothing could ever escape from within an event horizon. It was Hawking's own attempt to definitively disprove Bekenstein's idea by working out the quantum mechanical details near an event horizon as rigorously as possible that led him instead to discover Hawking radiation in 1974, providing exactly the physical mechanism Bekenstein's proposal had required but never itself explained, and vindicating Bekenstein's original insight so completely that the resulting formula for a black hole's entropy is now known jointly as Bekenstein-Hawking entropy, a specific, quantifiable value calculated from the event horizon's surface area that remains one of the most important individual equations connecting gravity, thermodynamics, and quantum mechanics anywhere in modern physics, and a genuinely rare case in the history of science, where a theorist's attempt to refute a colleague's idea ended up providing its most important confirmation instead. Physicist Don Page, who had worked as a graduate student under Hawking during the original development of Hawking radiation, made a further theoretical contribution in 1993 that would only prove its full significance decades later, calculating precisely how the quantum entanglement between a black hole and its emitted radiation should evolve over the entire course of the black hole's evaporation, assuming, as quantum mechanics' unitarity principle requires, that information is genuinely preserved. Page's calculation predicted a specific curve, now called the Page curve, in which the entanglement between the black hole and its radiation should rise for roughly the first half of the evaporation process before turning around and steadily decreasing back toward zero as the black hole finishes evaporating entirely, a turning point now called the Page time, occurring at the specific moment when the black hole has radiated away exactly half of its original entropy. For decades, this remained a clean theoretical prediction that no one could actually derive from first principles calculations of an evaporating black hole using the tools available at the time, and it was precisely the more recent replica wormhole calculations mentioned later in tonight's video, developed from around 2019 onward, that finally allowed theoretical physicists to derive a Page curve-like result directly from a more careful, more rigorous treatment of the underlying quantum gravity, providing exactly the kind of specific quantitative confirmation that information preservation advocates had been seeking for more than a quarter of a century since Page's original, prescient 1993 calculation. The discovery that black holes possess a genuine thermodynamic temperature and slowly evaporate, discussed in the previous chapter, led directly to one of the deepest unresolved problems in modern theoretical physics, one that has occupied some of the field's sharpest minds for half a century without a fully settled resolution. The black problem, stated simply, goes like this. Quantum mechanics contains a principle considered close to sacred among physicists called unitarity, which essentially guarantees that information is never truly destroyed in any physical process. In principle, if you had complete perfect knowledge of a system's final state, you could always, at least mathematically, reconstruct exactly what its initial state must have been, tracing the process backward with total precision. Every confirmed law of quantum physics respects this principle rigorously. But Hawking's 1974 calculation of black hole radiation suggested something that appeared to directly violate it. The radiation a black hole emits as it slowly evaporates appears to be almost perfectly random and featureless, carrying essentially no detailed information about whatever specific matter originally fell into the black hole to form it. If a black hole eventually evaporates completely, and the radiation it leaves behind genuinely contains no trace of what fell in, whether it was a star, a spacecraft, or a library's worth of books, then the information describing that original matter appears to have been permanently and irretrievably destroyed, a direct and troubling violation of one of quantum mechanics' most foundational principles. This apparent contradiction, first clearly articulated by Hawking himself in a 1976 paper, sparked decades of intense debate, sometimes genuinely heated, within the theoretical physics community over which of two extremely well-tested theories, general relativity's confident prediction about how black holes and their radiation behave, or quantum mechanics' equally confident insistence that information cannot be destroyed, would ultimately have to give way. Neither theory has ever failed an experimental test within its own domain, which is precisely what makes their apparent disagreement here so genuinely troubling to physicists, rather than merely an academic curiosity. Considerable theoretical progress has been made since the 1970s, even without a fully settled resolution. One especially influential idea, called the holographic principle, developed significantly through work by physicists Gerard 't Hooft and Leonard Susskind, beginning in the early 1990s, proposes that all of the information describing everything that falls into a black hole is, in some genuinely strange sense, encoded not in the black hole's three-dimensional interior at all, but on the two-dimensional surface of the event horizon itself, in a manner mathematically analogous to how a two-dimensional hologram can encode a full three-dimensional image. If correct, this would suggest that Hawking radiation emitted from the horizon could in principle carry away the information encoded there after all, just scrambled into an extraordinarily complex, effectively unreadable pattern rather than genuinely destroyed, preserving unitarity but making the information practically, if not fundamentally, irretrievable using any realistic instrument. Hawking himself, notably, changed his own position on this question over time. After decades of arguing information genuinely could be lost, he announced, in a widely reported 2004 talk, that he had come to believe information was likely preserved after all, conceding a long-standing informal bet on the subject with fellow physicist John Preskill, and paying up, according to the terms of that specific wager, with an encyclopedia of baseball statistics from which information can be recovered at will, a characteristically wry touch to a debate that had occupied serious physicists for 30 years by that point. More recent theoretical work, particularly developments from around 2019 onward, involving mathematical objects called replica wormholes within certain simplified models of quantum gravity, has provided increasingly detailed technical arguments suggesting information can indeed be recovered from evaporating black holes in a way consistent with quantum mechanics, calculations that many theoretical physicists consider genuinely significant progress toward resolving the paradox. It's important to be precise, though, about the current state of this research. These results have mostly been derived and rigorously demonstrated within simplified, lower-dimensional toy models of gravity that are more mathematically tractable than our full, four-dimensional universe, and extending them with full rigor to realistic, astrophysical black holes remains active, ongoing work rather than a fully settled, completed result. The honest current status of the information paradox, as of the most recent research, is that most theoretical physicists now lean toward believing information is ultimately preserved consistent with quantum mechanics, but the precise mechanism by which this happens, worked out in complete, rigorous detail for a real, physical black hole, is not yet something the field has fully agreed upon or definitively demonstrated. A particularly sharp version of the information paradox, called the firewall paradox, emerged in a 2012 paper by physicists Ahmed Almheiri, Donald Marolf, Joseph Polchinski, and James Sully, often referred to collectively by their initials as AMPES, who argued that several of the field's most cherished assumptions about black holes could not all simultaneously be true. The paper demonstrated, through a careful chain of reasoning, that preserving information in the way holographic principle suggests, while also keeping quantum mechanics unitarity intact, appeared to require that an observer falling across the event horizon would not experience the smooth, uneventful crossing described earlier in tonight's video at all, but would instead encounter a wall of extremely high-energy radiation, a firewall, right at the horizon itself, instantly destroying anything that touched it, a direct and startling contradiction of general relativity's own prediction that crossing a sufficiently large black hole's horizon should feel like absolutely nothing unusual. The firewall paper set off a genuinely intense round of debate within theoretical physics, since resolving it seemed to require giving up at least one of three separately well-established principles: the equivalence principle at the heart of general relativity, unitarity at the heart of quantum mechanics, or the specific way physicists had been applying the holographic principle to describe evaporating black holes. Several proposed resolutions have been advanced since 2012, including a considerably more exotic proposal from physicists Juan Maldacena and Leonard Susskind, suggesting that entangled black holes might be connected by microscopic, non-traversable wormholes, informally summarized in the phrase R equals EPR, linking the geometric wormholes first explored by Einstein and Rosen to the quantum entanglement first described by Einstein, Podolsky, and Rosen in an entirely different 1935 paper, a genuinely speculative but actively pursued idea that no version of the firewall debate has yet fully and conclusively settled. Before the firewall paradox sharpened the debate so considerably, in 2012, physicist Leonard Susskind had already proposed, beginning in the mid-1990s, an earlier and somewhat gentler resolution to the broader information paradox called black hole complementarity, arguing that the apparent contradiction and a distant observer watching Hawking radiation might not be a genuine contradiction at all, but simply two descriptions that are each fully valid and fully consistent within their own separate reference frame, provided no single observer could ever actually compare notes between both perspectives directly. Under complementarity, information about infalling matter could, from a distant observer's point of view, be considered smeared thinly across the event horizon and eventually released in the outgoing Hawking radiation, while the same infalling observer would, from their own perspective, experience that same information falling smoothly through the horizon and continuing on toward the singularity, with no genuine physical paradox arising specifically because relativity itself already tells us that different observers can legitimately disagree about the timing and location of events, provided their two accounts could never actually be cross-checked against each other by any single physical observer occupying both vantage points simultaneously. Complementarity held up reasonably well as a working framework for nearly 2 decades, and it's precisely this framework that the 2012 Firewall paper directly challenged, arguing that a sufficiently careful accounting of quantum entanglement showed complementarity's two perspectives couldn't actually both remain fully consistent. After all, reopening a debate many theoretical physicists had considered, if not fully closed, then at least reasonably well managed for the better part of 20 years. A genuinely striking and genuinely controversial recent development in this debate arrived not from a telescope or a particle accelerator, but from a quantum computer. In a 2022 paper published in Nature, a research team led by physicist Maria Spiropoulou, working with Google's Sycamore quantum processor, programmed a small number of quantum bits to simulate a simplified, highly idealized model of a wormhole, then encoded a small piece of information into one side of the simulated system and observed it emerge, transformed but recognizably intact, on the other side in a manner the team argued was consistent with the theoretical predictions of the ER's EPR framework connecting wormholes and quantum entanglement discussed earlier in this chapter. The experiment generated immediate and considerable excitement in popular science coverage, with some outlets describing it, not entirely accurately, as physicists having created and sent information through an actual wormhole, a characterization the research team itself, along with numerous outside theoretical physicists, quickly and firmly pushed back against, clarifying that the experiment simulated an extremely simplified toy model on a 9-qubit quantum processor, a system far too small and far too simplified to represent anything resembling an actual astrophysical wormhole or a realistic model of quantum gravity. The experiment's genuine scientific value, according to most physicists who examined it carefully, lies in demonstrating that certain specific, mathematically precise predictions about information transfer in these simplified gravity-adjacent models can be tested directly using existing quantum computing hardware, a genuinely useful new experimental tool for probing extremely simplified analogs of quantum gravity questions, even while the gap between this small-scale simulation and any actual astrophysical black hole remains, by the researcher's own account, considerable. Not every supermassive black hole sits quietly at the center of its galaxy the way Sagittarius A currently does. When a supermassive black hole is actively consuming large quantities of surrounding gas and dust, the resulting object can become one of the most luminous phenomena in the entire universe. A quasar, short for quasi-stellar radio source, a name reflecting the fact that when these objects were first discovered in the early 1960s, astronomers initially mistook their intense, point-like brightness for unusually strange stars within our own galaxy, before later work revealed they were actually the blazing cores of galaxies, billions of light-years away. The mechanism powering a quasar's extraordinary brightness involves what astronomers call an accretion disk, a swirling, flattened disk of gas and dust spiraling inward toward the central supermassive black hole, heated by friction and gravitational compression to temperatures reaching millions of degrees before finally crossing the event horizon. This superheated material radiates enormous amounts of energy across the electromagnetic spectrum, from radio waves through visible light and into X-rays, and the total light output of an actively feeding quasar can outshine every one of the hundreds of billions of ordinary stars in its host galaxy combined. Despite originating from a region of space not much larger than our solar system, tucked at the very center of a galaxy that may span 100,000 light-years across. Some of the most luminous quasars also produce powerful jets of superheated plasma, launched from the immediate vicinity of the black hole and accelerated to speeds approaching the speed of light, extending outward for hundreds of thousands, and in extreme cases millions of light-years, vastly larger than the host galaxy itself. The precise physical mechanism launching these jets remains an area of active research, but it's generally understood to involve a complex interaction between the black hole's rotation, discussed in Chapter 7, and powerful magnetic fields twisted and amplified within the surrounding accretion disk, a process related to, though considerably more complex than, the theoretical Penrose process discussed earlier, and one that some physicists consider among the most efficient energy conversion mechanisms known anywhere in the universe. The most massive black hole reliably identified through quasar observations, catalogued as Tion 618, is estimated at a genuinely staggering 40 billion solar masses or more, based on the width of specific emission features in its light spectrum, a mass so extreme that its event horizon alone, if placed at the center of our solar system, would extend well beyond the orbit of Neptune. Objects on this scale push the outer boundary of current theoretical models, attempting to explain how black holes can grow large enough, quickly enough, to reach such extraordinary masses within the finite age of the universe, a puzzle directly connected to the early universe formation questions raised back in Chapter 3. Quasars also offer astronomers a genuinely valuable observational tool precisely because of their extreme distance and brightness. Because light takes time to travel across the universe, observing a distant quasar means observing it as it existed billions of years in the past, and the most distant confirmed quasars, detected at redshifts corresponding to when the universe was less than 700 million years old, provides some of the most direct evidence available that supermassive black holes were already forming and actively feeding remarkably early in cosmic history, reinforcing just how puzzling and unresolved the question of their rapid initial growth genuinely remains. Our own Milky Way's black hole, quiet and comparatively modest Sagittarius, is not currently in a quasar-like feeding state, and hasn't been for a very long time based on available evidence, though some researchers have proposed, based on indirect evidence, including certain large-scale gas structures observed above and below the galactic plane, that it may have gone through a more actively feeding phase, producing something resembling a much smaller-scale quasar outburst at some point within the past several million years. A genuinely speculative but actively researched possibility, resting on indirect geological and gas dynamical evidence rather than any direct historical observation, since no human observer or any observer at all, as far as we know, was present to witness it directly. A supermassive black hole doesn't need to be feeding continuously to briefly outshine its entire host galaxy, and one of the more dramatic ways an otherwise quiet black hole can suddenly flare to life is through what astronomers call a tidal disruption event, occurring when an ordinary star wanders too close to a supermassive black hole and is torn apart entirely by the black hole's tidal forces. The same basic stretching effect responsible for spaghettification, discussed earlier in tonight's video, but acting here on a whole star at galactic scale rather than a falling human body. Roughly half of the star's shredded material is typically flung outward and lost to space, while the remaining half falls inward, forming a temporary, extremely bright accretion disk that can, for a period of weeks to months, cause an otherwise dormant galactic center to briefly rival the brightness of an actively feeding quasar before fading back into quiet as the available stellar material is fully consumed or dispersed. One of the most thoroughly studied examples, an event catalogued as ASSN14 and detected in 2014 by the All-Sky Automated Survey for Supernovae, was observed across X-ray, ultraviolet, and radio wavelengths simultaneously, allowing astronomers to directly trace the entire sequence from the initial disruption through the formation and gradual settling of the resulting accretion disk in a level of multi-wavelength detail no tidal disruption event before it had ever received, and the sheer rarity of these events, estimated to occur only once every 10,000 to 100,000 years for any individual galaxy, means each newly detected case offers astronomers a genuinely valuable and infrequent opportunity to study how a supermassive black hole's surrounding accretion disk actually forms and evolves in close to real time, rather than being observed only in the comparatively stable, already established feeding state quasars typically present. Whether an actively feeding supermassive black hole appears as a quasar or as one of several related but distinctly named categories astronomers use, depends heavily on a single factor: the specific angle at which we happen to be viewing it from Earth. Blazars, among the most extreme and energetic objects known to astronomy, are understood to be ordinary active supermassive black holes whose relativistic jet, of the kind discussed earlier in this chapter, happens to point almost directly at Earth, an alignment that dramatically amplifies the jet's apparent brightness and causes its light to vary unpredictably on timescales of hours or even minutes through an effect called relativistic beaming, closely related to the same beaming effect responsible for the asymmetric brightness of the ring seen in the Event Horizon Telescope images discussed earlier in tonight's video. Seyfert galaxies, first systematically catalogued by astronomer Carl Seyfert in 1943, decades before quasars themselves were identified, represent a comparatively less extreme and considerably more common category in which a supermassive black hole is actively feeding, but at a more modest rate, producing a bright, compact central nucleus without the jet or overwhelming total luminosity that defines a true quasar. And current unified models of active galactic nuclei propose that quasars, blazars, and Seyfert galaxies may, in a meaningful number of cases, represent fundamentally the same basic underlying phenomenon: an actively feeding supermassive black hole surrounded by a dusty torus of obscuring material, simply observed from different viewing angles and at different specific feeding rates, rather than representing genuinely distinct categories of object, each requiring its own separate physical explanation. Among the specific record holders for cosmic distance, a quasar catalogued as ULAS J1120 641, discovered in 2011 through a systematic survey of the United Kingdom Infrared Telescope Deep Sky Survey, and announced by a research team led by astronomer Daniel Mortlock, held the title of most distant confirmed quasar for several years, observed as it existed when the universe was only about 770 million years old, powered by a central black hole, estimated at roughly 2 billion solar masses. Discoveries since, particularly aided by the James Webb Space Telescope's infrared sensitivity, following its 2021 launch, have pushed the confirmed distance record for actively feeding supermassive black holes. Even further back, into the universe's first few 100 million years, each new record consistently reinforcing the same basic puzzle raised earlier in tonight's video regarding how a black hole could plausibly grow to billions of solar masses within such a comparatively brief cosmic timeframe. Quasars at these extreme distances also provide astronomers with an once upon a time, entirely separate and genuinely valuable scientific tool, since their intense light passes directly through the vast intervening stretches of early intergalactic gas on its long journey to Earth, and detailed analysis of exactly which specific wavelengths of that light have been absorbed along the way allows astronomers to study the physical and chemical state of the universe's very earliest gas, including direct evidence for the specific era known as reionization, when the first stars and galaxies emitted enough ultraviolet light to strip electrons from the universe's neutral hydrogen for the first time since the Big Bang, transforming the early universe from a fog opaque to visible light into the transparent, star-filled cosmos observable today. We've covered a great deal of ground tonight, from the basic physics of an event horizon, through the death of massive stars, the different size categories black holes occupy, the black hole anchoring, our own galaxy, the first direct photographs ever taken of one, what falling into one would actually involve, the strange physics of rotation, the sound of two of them colliding captured for the first time in 2015, their slow theoretical evaporation, and the still unresolved question of where their information ultimately goes. It's worth closing by being honest about the genuine boundaries of current knowledge, because black holes remain one of the very few places in modern physics where confirmed observation and unconfirmed theory sit this close together. The singularity at a black hole's center remains, by most physicists' own admission, more a placeholder for our theoretical ignorance than a confirmed physical description of what's actually there. General relativity predicts infinite density and infinite space-time curvature at that point, but nearly every physicist working in the field considers this a signal that general relativity itself is being pushed well beyond the conditions it was ever designed to handle, rather than a literal, physically accurate description of reality. What actually replaces that infinity, whether some form of quantum gravity smooths it into something finite, whether string theory's proposed extra dimensions somehow resolve it, or whether some entirely different framework not yet developed is required, remains genuinely unknown and is widely considered one of the most important open problems in all of theoretical physics. Closely related is the mathematical possibility of what physicists call a naked singularity, a theoretical singularity that would exist without an event horizon surrounding and concealing it, meaning it would, in principle, be directly visible and observable from the outside universe, rather than permanently hidden beyond a point of no return. Roger Penrose, whose 1965 work proved black hole formation was a robust, essentially unavoidable prediction of general relativity, also proposed what's now called the cosmic censorship hypothesis, the conjecture that nature always hides singularities behind event horizons, forbidding naked singularities from forming under any physically realistic conditions. Despite considerable theoretical effort over more than 5 decades, this hypothesis has never been rigorously proven as a general mathematical result, nor has it ever been disproven, and it remains, remarkably, one of the significant open conjectures in classical general relativity, even today. White holes represent another genuinely fascinating theoretical curiosity, worth mentioning honestly for what they are. A mathematical solution to Einstein's equations that behaves essentially like a black hole running in reverse, a region from which matter and light could only ever emerge, and into which nothing could ever fall. White holes arise as legitimate solutions within the mathematics of general relativity, and are even connected, in some theoretical treatments, to certain solutions describing rotating Kerr black holes discussed in Chapter 7. However, no white hole has ever been observed, and most physicists consider them highly unlikely to exist as stable, physically realistic objects in our actual universe, in part because any small perturbation appears likely to destabilize the delicate mathematical conditions required to sustain one, making white holes a legitimate, still studied mathematical possibility, but very much not an established astronomical phenomenon. Wormholes, similarly, remain firmly theoretical. Certain solutions to Einstein's equations, first explored in a specific form by Einstein and physicist Nathan Rosen in 1935, describe a theoretical bridge connecting two distant, or even entirely separate, regions of space-time. No physical mechanism for creating or stabilizing a traversable wormhole, one that wouldn't collapse instantly under its own gravity before anything could pass through, has ever been demonstrated, and most theoretical work suggests doing so would require some form of exotic matter with genuinely bizarre properties, including negative energy density, that has never been confirmed to exist in any form suitable for the purpose. Wormholes remain a legitimate and actively studied subject in theoretical physics, connected to serious ongoing research into quantum gravity and the holographic principle discussed in Chapter 10. But they remain, as of current physics, squarely in the realm of mathematical possibility rather than demonstrated reality. There is a genuinely calming thought to end on in its own way, buried inside all of this uncertainty. Despite everything, we still don't know about what happens at a singularity, whether naked singularities can form, whether white holes or traversable wormholes could ever exist. The parts of black hole physics we do understand with confidence have been tested against reality again and again, and have passed every single time. In the orbit of a star called S2 circling our galactic center, in a photograph of a shadow 55 million light-years away, in a trembling of space-time itself first detected in 2015, arriving after traveling for over 1 billion years to reach 2 4-kilometer tunnels built specifically to notice it. The universe built objects strange enough that 18th-century clergymen could only guess at them. Mathematically, that Einstein himself doubted could truly exist, and that we can now, in a very real sense, both photograph and listen to. Let the scale of that settle over you now, along with everything still left unanswered at the very center of the dark. There's something quietly steadying in noticing how many of tonight's 200 facts trace back to a scientist willing to sit with an idea, long after everyone around them had stopped taking it seriously. John Mickle guessed at dark stars in 1783 and was mostly forgotten for a century. Carl Schwarzschild worked out his solution from a wartime trench and died before anyone called it anything close to real. Jacob Bekenstein proposed black holes carried genuine entropy, while the field's most famous physicist publicly argued he was wrong, and turned out, in the end, to have been right first. None of them knew in the moment that a photograph would eventually exist, or that space-time itself would eventually be heard trembling, or that a graduate student's laptop would one day light up with the actual image they'd only ever had equations for. They simply kept working the problem in front of them, carefully for its own sake, without any guarantee the universe would ever hand back a confirmation. There is nothing left to calculate tonight, nothing left to measure, nothing left to do but let the weight of all that gravity, all that bent and folded space-time, pull you gently down into a rest as quiet and complete as the space beyond an event horizon itself.